right, we are back after spring break and ready to start our new unit on gases and the kinetic theory. So here we go. What is a gas? Gases are molecules that move freely. That means there's very little forces of attraction between them. They are molecules that have a large amount of kinetic energy. They're moving about very quickly, and they take the shape of the container that they are in. They fill up the volume of the container. They have lots of empty space between the particles. And because they have lots of empty space, they're easily compressed. That means you can squish them into smaller spaces. You can push them together because there's all that space in between them. So the kinetic theory, or the kinetic molecular theory, so if you see it abbreviated KMT for short, states that all particles are in constant motion. And that particles in a gas are usually molecules or atoms. Not formula units. Formula units are reserved typically for solids because those are your ionic compounds. Ionic compounds aren't going to be in the gaseous state. As temperature increases, our kinetic energy increases. There are three assumptions about gases. Assumptions are things that we take to be true. The particles of a gas contain such particles, and we assume their volume to be insignificant. It means we can kind of ignore them. So that means that they don't take up any space. The movement of gas particles is rapid, constant, and random. They move extremely quickly. They travel in straight lines and do not stop. They will change direction only after they bounce off of something else, if they hit something, basically, or the walls of the container, and they fill all the available space in a container. Gas particles experience elastic collisions. Elastic collisions mean there is no energy transferred from particle to particle with when they collide. There's no loss of energy. Energy is conserved. The next section right here in this box looks at the difference between ideal and real gases, and we are going to skip that section. We're going to take that section out. It's something that we're going to kind of omit for time's sake this year. But as far as the pictures go, first little thing here with this is an arrow. The particles of gas are so small they do not take up a lot of room in the container. So again, in between, a lot of empty space. In the second picture, they're taking up, again, not as much space within the container, and you can see that they're moving around, and they fill the space they're in. And that word we're going to add here, it goes along with that, is the word diffusion. So when they fill the space they are in, that's called diffusion. On to the next page. What is gas pressure? It's a result of rapidly moving particles in a gas simultaneously colliding with an object. Pressure is based on the number of collisions. Sometimes we talk about a gas compared to in a vacuum. Vacuum is when there is an empty space, when there are no particles. And if there's no particles, then there can be no pressure. So the absence of particles the absence of a gas in a container would be in a vacuum. The SI unit for pressure is the Pascal, and SI, if you remember at the very beginning of the year when we studied the metric system, stands for the System International. It's the revised metric system. And so conversions are back because we have a lot of pressure conversions here. We have the main one that we usually deal with is the atmosphere, and that is compared to everything else here. 1 atmosphere is 101.3 kilopascals, so obviously that is a 1,000 pascals. That's related to the millimeter of mercury. That's a height of a column of mercury. A millimeter of mercury was renamed after an Italian physicist by the name of Torricelli. So a 1 millimeter of mercury is the same thing as 1 torr. They're exactly the same thing. And then PSI stands for pounds per square inch. So PSI that's what that stands for. And then you have bars, 1.0 or 1.013. I don't use bars that much, but just in case you hear that. We occasionally measure things at what we call STP. S stands for standard, T stands for temperature, and P stands for pressure. There goes my clock, I apologize. 0 degrees Celsius is standard temperature. 1 atmosphere is standard pressure. Pressure is based on the number of collisions. So if you imagine the gases colliding with the wall, then it is, if you think of physics kind of, it's dealing with the force exerted over a given area. So we're going to practice then just some conversions with units of pressure. We're always going to try and make these into one-step conversions. So if a pressure gauge records pressure to be 450 kPa, so that's our given, 450 kilopascals. So we know from dimensional analysis the kPa's are going to go on the bottom. They want to know it in atmospheres, so atmospheres would have to go on the top because that's what we're trying to find. So we go up to the top and we know atmospheres. Here I'm circling atmospheres and kPa's. And we know 1 atmosphere, so I'm going to put that on the top, is equivalent to 101.3 kPa. So, because 101.3 is on the bottom, I'm going to divide by that. So I take 450 in my calculator, divide it by 101.3, and I get 4.44 ATM. ATM is the abbreviation for atmospheres. So that's my answer. In the next one, my given, again, 450 kPa. I put kPa on the bottom because I want to get rid of kPa. I'm solving, in this case, for millimeters of mercury. So I'm going to go up to the top. I'm going to change my color to green. I'm going to find kPa. And now I'm going to find millimeters of mercury. By kPa, I'm going to put the 101.3 kPa, and now it's equivalent to 760 millimeters of mercury. So I'm going to take my calculator, I'm going to punch in 450. I'm going to multiply it times 760 because that's on the top, and then I'm going to divide it by 101.3 because that's on the bottom, and I'm going to keep 3,376 as my answer, millimeters of mercury. And that is all. We will practice these again later on in the week after we take our stoichiometry test. Thanks for listening.